Good morning, and thank you for joining me online. I'm assuming you're here at the morning. You could be here at the afternoon. I'm not sure what time of the day it is for you, but it's certainly the morning for me right now as I'm recording this. Today we are switching into the second chunk of Chapter 6, Section 6.2.1. The title is How Can I Solve the System? And today we're focusing on something we're going to call the equal values method. Equal values method. And the idea goes something like this. If two things are equal to the same thing, then they're certainly equal to each other. I guess an example. If I told you that A was equal to 5, and I told you that B was equal to 2 plus 3, well, because 2 plus 3 is 5, and because 5, of course, is truly equal to itself, it follows that the thing that's equal to 5, A, must also be equal to the other thing that's equal to 5, B. So that's the idea that we use when we deploy this method called the equal values method. So let's consider the following system of equations. Y is equal to 3x plus 5. And we have another equation, y is equal to negative 8x plus 25. Now, while it's true that I could absolutely graph those two equations, and we could look at where the solution is. In fact, let's do that real quickly. So I'll go ahead and type the first equation. It was y is 3x plus 5. Beautiful. And the other one was, well, y is negative 8x plus 25. There it is. I can see where the solution is. The problem that I have with this particular solution, and if I hover over Desmos I can see it, it's not a nice number, right? Those are not decimals that I easily recognize, and even though they terminate at a few decimal points here, they continue on forever. Desmos is just rounding off. So graphing is certainly a powerful technique for a couple things. Sometimes your answer is going to be obvious. It'll be at a point and you can clearly identify the integers or maybe even some small fractions. But when the answer gets to something like this and you need precision, we're not going to want to use a graphing technique. We're going to want to use this thing I'm going to call the equal values method. So let's go back to our notebook. So what we do is we realize, oh, hey, y, in the context of this problem, y is certainly equal to itself. And I can see that, well, on the one hand, y was 3x plus 5. And on the other hand, y was the opposite of 8x plus 25. So because these two things are both equal to y, because the expression underlined in blue is equal to y, and because the expression underlined in red is equal to y, it must be the case that those two expressions are equal to each other. So I write that 3x plus 5 must be the same as the opposite of 8x plus 25. And if I go ahead and add 8x to both sides, I get 11x plus 5 is 25. Therefore, 11x is the number 20. And dividing by 11, I get that x must be 20 over 11. So if I come back over to Desmos, I'm going to try this, and if I type, okay, x equals 20 divided by 11, yeah, I can see absolutely that is the x value where those 2 points meet, right? So that number for x 1.8182, right, is really this number. It repeats. And we could, now that we know what x is, right, we know that x is 20 over 11. I have two different ways to figure out what y is, and it doesn't matter which one I use. I could either use the expression I underlined in blue or the one I underlined in red to calculate what y is. Let's try the one that I underlined in blue. I could say, hey, y, according to the expression up there in blue, y was 3 times x plus 5. Well, I know what x is, so I can say, oh, y must be 3 times 20 over 11 plus 5. This doesn't look like it's going to be pretty. Let's see, 3 times 20 over 11 is 60 elevenths plus 5. If I want to combine those two things, they need to be both elevenths. So I'll say y is 60 over 11 plus, this would have to be 55 over 11. So what I did is I multiplied this number 5 by 11 over 11 to get common denominators. If I combine those two things, that's going to be 115. I get that y is 115 over 11. Not a pretty answer, and I'm sorry that it's not a pretty first example, but I think a lot of times when we look at these things and it's just like, oh, I could graph it and it's easy, but we don't focus on the technique. So I really want to look at this technique and encourage you to deal with this, because an equation like this is the one where you really need all the tools. So my answer is these two lines, the two original lines, right, are going to meet. They're going to meet each other at the point when x is 20 over 11 and y is 115 over 11. Let me confirm that other point. Let's go and write here. Y is equal to 115 divided by 11. And there you go. You can clearly see that the black line and the blue line, right, this is the x value that we found, and this is the y value. So this point is absolutely x is 20 over 11 and y is 115 over 11. So make sure you have this example in your notes, and if you need to, flip it back real quick and watch this again. But again, the idea here is that when you have two expressions that are equal to the same thing, those expressions must be equal to each other. So in our original problem, because the expression 3x plus 5 and the expression the opposite of 8x plus 25 were both equal to y, they must be equal to each other. And then from that point, because they are equal to each other, right, we can set them equal to each other and then solve in this case for x, and then we can use that value of x in either one of the original equations to calculate y. Moving on to our next example, problem 44, 6-44. So this is a definition of what a systems of equation is. It says a set of two or more equations with the same variables is called a system of equations. When you set the two expressions that are equal to the same variable equal to each other, like you did in the previous lesson and the example I just gave you, we're using something we'll call the equal values method of solving a systems of equations. Use the equal value method to solve the following problem. So in this problem we have to write the system first, and then we have to use that system we write to solve. So it's time to cool off on a hot summer day. Team Sunshine, because I always hang out with kids that call themselves Team Sunshine. Team Sunshine is filling an inflatable kiddie pool from a garden hose. The pool has 30 gallons in it, and Team Sunshine is adding 8 gallons per minute with a garden hose. So right now, I'm going to be using the same variables for both. So I'm going to write this let statement. I'm going to say let, not lex, let x equal time filling pool in minutes, and y is going to equal the water in pool. So for Team Sunshine, we can say that the amount of water in the pool y is equal to, let's see, the pool has it has 30 gallons already, so we've got a y-intercept of 30 and we're adding 8 gallons per minute. So we'll say 8x because each minute gets 8 more gallons plus 30. So that's Team Sunshine. Next door, Team Breezy's pool is already filled with 180 gallons of water. They are emptying the pool at 5 gallons per minute with buckets. Geez, guys, take the water next door if you're done. Okay, so this is Team Breeze. Breeze. They are decreasing the water in the pool. They are taking out 5 gallons every minute, and they have a total of 180 gallons in the pool to start with. So this is our system of equations. And because, like our previous example, we have the case that I have this expression that is equal to y, and I have this expression that's equal to y. And because y is equal to y, right, these two values are equal to each other. So I can say that 8x plus 30 must be the same as negative 5x plus 180. Therefore, let's add 5x to both sides. 13x plus 30 is 180, right? 5, 8, 9, 10, 11, 12, 13, yeah. And I'm going to take away 30 from both sides, so I get that 13x equals 150, and therefore it looks like x is 150 divided by 13. And because I have a nice let statement up above, I understand that this is the amount of time. And if I do this, it's 11.5. So it's about close, it's almost 12 minutes. 11 minutes, 30 some seconds, or about 12 minutes. So x is about 12 minutes. So the problem also says to check your work, and I think that's an important thing to think about as we start this new semester. Once we're done, right, what do we do for the aftermath? So math has already happened, so what about the aftermath? Well, something that should be true is if I place this value into each of these expressions, I should get values of y that are very close to each other. So for example, if I could take the 8 times 150 divided by 13, and then I will add 30 to that, and you can see I get about 122.307. Same thing, I'll do 5, negative 5 times, and I have to go again 150 divided by the 13, and I'll add 180 to that, and I get the same thing, 122.307. So this value of x makes both of these expressions equal to each other. So at time, about 12 minutes, the pools will have the same amount of water in them. Okay, I think this is our second to the last example, 45, the tortoise and the hare. So yesterday, when they talked about it was a family that was camping, and I went through several examples of this recurring rate this recurring problem observation that if you take a speed, for example, 55 miles per hour, and you multiply the 55 miles per hour times 2 hours, right? And I could think about 2 hours over 1. When I multiply a speed times an amount of time, the units of time cancel, and I'm left with a distance, right? So we're going to take this as a relationship that a speed or a rate times an amount of time is equal to distance, right? So we'll keep coming back to that. That's something that we need to remember from dimensional analysis, is that distance times distance equals rate times time, and probably that's normally how we would see this written, but nope, distance equals rate times time. So that's something to squirrel away in your notes. But then also there's a lot of variations of that. I could solve for r in that equation. I could also solve for t. So let's take a look at this problem. The tortoise and the hare are having a race. I've heard of this. In this tale, the tortoise moves at 50 feet per hour, while the hare moves 250 feet per hour. Okay. They're both being expressed in feet per hour, so the units are consistent. The tortoise takes 8 hours longer than the hare to finish. What was the distance of the race? Okay. let's see, let t represent an unknown time in hours that it took the hare to complete the race. Write an expression, not an equation, representing the time it took the tortoise to finish the race. So I will typically, if I see a problem like this, I might organize my work in a table like this. And if you find this helpful, that's great. If you don't need to use this. But for me, there's two people, right? I've got the tortoise, Tortois, and I've got the hare, Hare. And we have a distance, we have a rate, and we have a time. And for the tortoise, I do know the tortoise's rate. The tortoise is slow. The tortoise is moving at a rate of 50 and then feet per hour. That's terrible looking. Let me make this bigger. And then the hare is traveling at 250, and again also feet per hour. So I know those things. And then they tell me let t represent the unknown time in hours that it took the hare to complete the race. So this column is time, right? And they're telling me that I'm going to let t be the amount of time, the unknown time that it took. Oh no, let t represent in hours that it took the hare to complete the race. So my bad. I need to put the t here. So t is the amount of time it took the hare to complete the race. And then in question A, it says write an expression, not an equation, representing the time it took the tortoise to finish the race. Okay, well, it says that the tortoise takes 8 hours longer than the hare. So if the hare takes t hours, the tortoise is going to take 8 more than that. So I'm going to say 8 plus, or t plus 8, right? 8 more than t. Now, the thing about this problem is that the distance they're traveling is the same, right? It's a race, and it's not like the trike races where someone had a head start, or the race is the same length for both the tortoise and the hare. So I could just put a D for both of these. Now, with this information organized and the fact that we know that the distance traveled is equal to a rate times a time, I can write the following equation. I can say that the distance for the tortoise is 50 feet per hour times the quantity t plus 8. And for the hare, I can say the distance traveled is equal to 250 feet per hour times t. So this is my system of equations, and I want to figure out, it says, it's asking what the distance of the race is. So I do have two equations here. B says write two equations that represent the race, one for the hare and one for the tortoise. And you can see how my table helped me organize that. And now question C is asking me to find the distance of the race, D. Well, in order to figure that out, I'm going to solve for t first. So certainly, because the distance of the race is the distance of the race, right? Because this d is equal to this d, it follows that 50 times the quantity of t plus 8 is the same as 250t. So if I distribute this, I don't need to distribute the 50, do I? I could divide both sides by 50. So if I divide this side by 50, this becomes a giant 1. And again, that's multiplication between those things, so it's legit. And then over here, 250 divided by 50, I get the equation that t plus 8 must equal is exactly 5. And don't forget there is a t there. If I subtract t from both sides, I get that 8 is 4t. And then therefore, dividing both sides by 4, I get that 2. T is 2. So the amount of time is 2 hours, but that's not the answer to the question, right? The question was how long is the race? And if I come back in here, the distance of the race is going to be the value I get when I plug 2 into these. And you can see if I plug 2 in for this value, right, when I plug 2 in there, this becomes 50 times 10, which was 500 units. I forget where these are clearly feet. Yeah, 500 feet. But also, if I plug 2 in for this value of t, I also get 500. So that's kind of a nice check that both of them did run 500 feet. It's just that the tortoise did it in more time. The tortoise did it in 10 hours, and the hare did it in only 2. All right, pretty much the final problem we're going to look at together is 46, and it's called mixing candy. Renard thought that writing 2 equations for problem 44 was easy. He wants to use 2 equations with 2 variables to solve this problem. Ariel bought several bags of caramel candy and several bags of taffy. The number of bags of taffy was 5 more than the number of bags of caramels. Oh, that's so hard for me to think about. Okay. So let's start with, I don't want to read anymore until I process that. So let's start with a let statement. Let C equal the number of bags of caramels, and let T equal the number of bags of taffy. And this says, I hope you're doing okay. I don't know if I am. That almost blew my mind. It says the number of bags of taffy was 5 more than the number of bags of caramel. 5 more than. Okay, so the number of bags of taffy was 5 more than the number of bags of caramel. There we go. I think that, okay, I'm feeling better now. So if I bought 2 bags of caramel, that would have to be 7 bags of taffy. Right? The number of bags of taffy was 5 more than the number of bags of caramel. Okay. More information. Taffy bags weigh 8 ounces each, and the caramel bags weigh 16 ounces each. The total weight of all the candy was 400 ounces. How many bags of each did she buy? Actually, that does not say. Having this let statement clear, in my mind, knowing exactly what those are really helps me process this. So I have bags of taffy and bags of caramel. The taffy are 8 ounces each. So I could say 8T, that's the weight of the candy from the taffy, plus we would say 16C, that's the weight of the candy from the caramels, and together that's 400 ounces. So here's the last thing that I want to point out today. So when we set up an equation like this, right, the thing is I don't have clear equal values, right? I don't have t equals something and t equals something. I've got this situation where I don't have clear equal values. But what I can do, certainly, is I can take this equation and I can solve it for t. So I'm looking at both sides of this, and it appears I could divide everything by 8. So if I divide each term by 8, it's going to become t plus 2c. And if I take the 40 and divide it by 8, it's not 40, it's 400. 400 divided by 8 is going to give me 50. And then if I subtract 2c from both sides, I get that t is equal to negative 2c plus 50. So at this point, I clearly have the situation where c plus 5 is equal to t and negative 2c minus 50 is equal to t. And because t is clearly equal to itself, I can take these two expressions and set them equal to each other. So c plus 5 is the same as negative 2c plus 50. Therefore, if I add 2c to both sides, 3c plus 5 is 50. Take away the problem, running out of room here. Take away 5 from both sides, I get that 3c is 45. And if I take 45 and divide that by 3, we get that c must be the number, well, let me write this, 45 over 3. I like you seeing that I'm seeing that step. C then equals 15. So I know that I have 15 bags of caramels. And if I want to figure out the number of bags of taffy, I'm just going to add 5 to that. So my bags of taffy is C plus 5, where C is 15, so this has to be 20. So the last question up here, it says, how can you verify that your solution's correct? Well, two ways, right? Certainly, this equation has to be true. If you take C and you add 5, you better get taffy. And I can see that that's the case. But the other thing that has to be true, let me grab a calculator. The other thing that has to be true is if I go 8 times T plus 16 times C, it better equal 400 rather. So I'll just go 8 times 20, 8 times 20, and then I'm going to add to that 16 times the number 15, and I get 400. So the question, how do I know? How can you verify that your solution is correct? By plugging in these two values, right, and seeing that it satisfies both of these equations. So answer, 15 bags of caramel and 20 bags of taffy. One last idea, and it is this. When you write equations to solve word problems, you sometimes end up with two equations like we ended up with in the candy above. So notice that the second equation is solved for y, but the first one is not, right? So our idea here is when we see that, wait a minute, it says notice that the second equation is solved for y, but the first is not. Okay, so the idea is when we see this, right, what we want to do is we want to get the first equation, in this case, into that y equals form. So in order to use the equal values method, like I would take this equation and say, oh, negative 2y is equal to the opposite of x plus 4, and then divide everything by negative 2. So y is going to equal negative x over negative 2 minus 2. That's divided everything by negative 2. And then I can clean this up, right? This is the same thing as positive 1/2 times x minus 2. So now that they're both in the form y equals something and y equals something, I can set those somethings equal to each other and solve for x and y. All right, so we're just about at 30 minutes. Thank you for watching and taking notes today. I hope you found that not stressful. And these notes will always live here. You can come back and review them later. Good luck on your homework today. I'll see you soon.